Hola, ¿cómo estás? How are you? Good morning. Wherever this will find you. We are going to go have some fun in PowerPoint for a while, and I'm going to do some demo from the PowerPoints. I'll try not to get too bogged down, and then we will go into ChatGPT and ask for a programming problem that I will model solving with you. So you have a little bit of something there. Uh, yeah, let's get started. Uh, we are now in the part of programming where things become fun because this is where you're learning about how to change the flow of your program. So I'm going to use that term often, the flow. And the reason that's kind of why we call it control structures is because you're controlling the flow of your program. And what is the flow of your program, you're asking? Well, just consider and think, we're talking about the CPU and how everything's a number and how things are loaded on the CPU, processed and offloaded, and everything uses a number. Okay, whatever. It's a mechanical thing. Uh, it's a process of loading, unloading, loading, unloading. That means it's progressive. That means it's linear. That means it does something. So the nature of programming is that mechanical flow of and control of what is actually being processed and put into memory. And that is done uh, one line at a time from top down. And that's why we call it top down programming. And so control structures, we're controlling the flow of the program. We're controlling what's loaded, what's unloaded, where it goes, and all kinds of, all that stuff. But it's really simple. It's a linear path. And I'm going to be harping on you on today, and every time that you sit down and talk with me, use the debugger because yeah, you're not really talking with me. Okay, we're moving on. I'm done. Let's get started. So control structures, what are they? They control the flow. And the first control structure is what we call an if statement. And that is done with mathematics so that you are making some kind of comparison, a numerical comparison, of course, with another number. And you're trying to determine how those numbers relate. And that is what we call logical operations with the logical operands and logical operators. There's even a full college course on just logic. Yeah, just going through logic using normal, kind of like English, but not code. But anyways, so the if statement, compares values and returns a true or false depending on what kind of what are you looking at for in that comparison. What are you looking for? And this is where your less than, greater than, equals, not equals comes in. And so we're going to be spending most of our time today on if statements. I don't want to get too bogged down on these PowerPoints. So I'm going to kind of, move forward through them. There's some other aspects to the chapter that we'll probably we may touch on as well. All right, so what is it? What is that flow? It's selecting how your program moves through these structures that we call control structures. But remember, mechanically, it's top down, and so we have what's called flow charts. And the flow in this case, the green arrow is the starting part. The flow is the arrows. This is the top down behavior of your program as it completes execution. So the flow, you see how these flow diagrams are showing different directions that the flow of your program can go and how it can move from top down as it normally mechanically moves line by line. And so you can actually modify how it moves line by line from top down. And that's what it is. So this is how your program uh, moves from line to line, and you can choose to skip some things and go around them and then continue on. You can choose to decide which direction you want to go with your flow, depending on an expression that we're going to be putting in an if statement, and that's going to be an operation, like a true false operation. And this comes from your greater than, less than type mathematics. Is eight is greater than 3, so then we use signs for that, and the signs, the operators we use come up in your operator precedence and associativity. Now, since we're going to actually be using this today, I'm gonna bring it up. It doesn't matter what language. Operator. Oh, I already typed it in for myself. Thank you, Josh. I appreciate that, especially when you're being lazy. Screw the Nah, maybe I should have went with the AI. Damn, so freaking dumb. Oh God. No, the AI sucks too. Okay, wait. Is this one better? Come on, give me some love. There we go. All right. So we see that expressions can be all kinds of different operators, but the expressions we use inside of an if statement are expected to be a true or false. We can use mathematics in those expressions, but they have to come down to a true or false by using a relational operator mixed in with maybe some logical operators that you may want to apply to it. So those are pretty much the different precedents for the operators that we're going to be using. Less than, relational operators have a higher precedence than logical operators. So now I want you to remember that, because we're going to come back to that. So logical operators happen after relational operators. And that's why, because they're in higher precedence. They're higher up in the chart. All right, we're going to come back to this when we start playing around and monkeying around with some code. And so the expression in the if statement is going to use a relational operator somewhere. So because a relational operator determines a true or a false. And an if statement, that's all it cares about. An if statement only cares that its mathematics inside of the if statement comes down and evaluates at some point to a true or false. That's all it cares about. And remember, a true is a 1. False is a 0. I'm going to be using that interchangeably, because literally when you look at in the code at the bottom, a true is actually 1. A false is actually the number 0. It literally is what it is. So even though we use the words true, false, whatever, by the way, that capital T is a dirty. That's a dirty. You're supposed to be lowercase, you silly thing. We're going to start with very simple operators, and then we're going to get a little crazy. We're going to have some fun. So let me kind of, let's bounce ahead a little bit, because this is where I want to actually start getting into showing you some examples I mean, I want to do a little demo. Because here's the if statement, and then yeah, flowchart. Okay, good. What else do we got here? Logical operators. That's great. We'll hit that at the same time. So these are used with the if statements, and okay, I can do better job showing you the demo than this PowerPoint stuff. Yeah. No, okay, there. Good. We're going to get to that point in demo mode, okay? And then we're going to come back and see if whatever we need to deal with after that. All right, so what do I mean by flow? Okay, so let's take this program for example. We're going to, we have a calculation for centimeters and a calculation for inches. Let's make these. No, this is good. This is good. Yeah. So let's just say that if, and this is where I put the expression. So this is going to be a very simplified form of the expression. If 4 is less than 0. Now I'm using literals. That means I'm literally typing in the numbers instead of putting like centimeters down here in place of the 4. And just ignore all this other stuff. We might end up using it in the demo later, as we progress. But I don't want to start out. I want to start out just very, very simple. In fact, let's just get rid of this crap. All right. So the program comes in. Let's say we do some things like, create an integer. We do some output, other stuff here, whatever. And we come into this if statement. So the program starts up here, continues down, hits this if statement. And then what it does is it evaluates, hey, with the CPU, it processes, is 4 less than 0? And that's going to return a false. So that's going to return a 0. And that's all the if statement cares about, because it's going to be what controls your flow. And when the if statement is true, your flow goes into these braces. Otherwise, it doesn't. It just continues on. Cout. Yes. And then let's set I equal to 45. Something like that. Whatever. I'm just putting in lines here so that I can show you how to, because we're going to debug. And I'm going to show you the flow. Okay, and then here we'll just say that I equals 34. And again, I'm just throwing in lines so that I can set a breakpoint and show you the flow. And then here I'm going to set I equal to 85. I'm just making up numbers. I'm just throwing in code here to show you flow. All right, I've said that 3 times. That's enough. Let's do demo mode. Okay, what mechanically happens with this if statement? Let's look at the very simplest form of an if statement, and that is meaning we literally put in true or false, because that's all it cares about. So right here I'm putting in false. Now you can do this properly, C++, false, but whatever. False, but 0. And what that's going to determine is, hey, how does the flow of your program run? Does the flow hit these lines or not? And these guys will only be run if this expression is true. So let's look at the flow. Because in this case, I'm literally setting it to false, and we're going to see what happens with the flow. Now, notice I put the breakpoint up here. And guys, use the stupid debugger. I mean, seriously, never mind. Start debugging. Okay. There we go. All right. Our flow starts at the top and works its way down. Now we're going to do a step over, which means evaluate that line and go to the next line. Okay, so now we go to the next line. There we go. We got our next line. We can even see what's going on down here with I. That's so cool. Debugging is the best. I is 34. Great. Okay, now we go here. Our flow sees this. And an if statement controls our flow. So it sees false and it says, oh, okay, I'm going to just ignore the code that's inside of the if statement scope. So this is the scope of the if statement start, the if statement end. Now, everything has its own scope. Main has its scope. It's a function. To have a start and an end down here. So does control structures. They have a beginning and an end. And only the end will only happen if, the inside will only happen if the if statement comes out as true. So let's look at this again. Step over, flow moves. Oh, it's false. Step over, skip all the way down. Boom, all the way down. It did not run these lines at all. It didn't run. And that's controlling the flow. Now let's modify that so you can see the difference. We're going to go true. Okay, now let's look at what happens. Okay, we go step over. Now we're true. Step over. Oh, yes, we visited them. We're actually running this code. Then we continue on and run the code down here. So you see the mechanical nature of it. And that's how you are able to do different things because you are controlling the flow of the program and the logic of the variables and how they are set. And all that with the mechanical flow, you're able to really come up with some high level tasks that the computer can carry out for you. And that's why we call them control structures. So let's extend this if statement into its other form, which means that what if we want to know both if the if statement contains a true or a false. We want to do something if the if statement is true, and we want to do something else if the if statement is false. Okay, so if the if statement's true, it's going to run this, just like we just showed you. Okay, and let's just be very purposeful here. Step over. Okay, it's true. Run this code, but this code only runs if it's false. And so it's going to skip over it because the if statement's true. Now, inversely, we set this to false. Step over. Now it's false. It skips over these guys and then runs into here. Oh, you silly goose. What did you do? I didn't get done. All right, there we go. Okay, false. All right, so that's the flow of. Well, okay, I've already talked to you about the super flow. That's it. That's how if statements work. That's how control structures do things, is by modifying your flow. And that's why we use debuggers, is so we can see it. So when I say see it, I mean that literally. You can see it. It's not hard. You got the best cheat sheet in the world. I dare you. Say cheat sheet 3 times fast. Cheat sheet, cheat sheet. Try it. Okay, never mind. All right. We're moving along. Let's see, where are we going? You know what? Let's delve into this, because those stupid PowerPoints are boring. Let's continue on with this, and we're gonna hit all the persnickety details on this statement, and then we'll go back to the PowerPoint and kind of finish up. So we're gonna concentrate on this part right here. This part right here is where students get the biggest hang up. Is kind of understanding how all that comes together, especially with that operator precedence and associativity chart. So let's dig into that, and let's take it to using the relational operators. Now this is your less than, or you're greater than, your alligators. Okay, that's better. And they have special syntax. They can only be used a certain way. And then there's the equals operator. Make sure, guys, that that's double equals. Okay, this is a common programmer's nightmare that happens always, especially in C++. Is often people will use the single equal sign there, and that's not a comparison operator. That's a relational. That's an assignment statement. So that's not a relational operator. It doesn't work with true or false. So you need to use double equals when you're comparing to see if 2 items are the same. And then there's the not equals, using the not equals, of course. Okay, but let's just get into it. Okay, this is the simplest form: 5 less than 6, and we know, okay, the computer is going to go in and it's going to evaluate this as true. It's going to say that that is a 1. And remember, guys, this is actually true. I'm using 1 instead. Okay, so we know that that's going to then trip. We do 5 less than 6. We can use literals like that, and it's going to evaluate as true. Okay, now I'll show you a little trick here. One thing you can do to get a little preview into what this is going to evaluate as, and I'm referring to where they're more complex, where we're actually using variable names, not actually literally typing in 5 less than 6. But you can select the whole expression and right click it and say add watch, and you see down here 5 less than 6 Boolean evaluates as true. So you can get an idea of what your expressions will evaluate as by just selecting them. So guys, you got the cheat sheet. It's here. It's here. The best way to take your tests is to have your compiler run, going off to the side. Yeah. So what would that look like? Okay, let's throw in a little more complexity. Let's throw in an int j and a float No, let's keep with ints. I want to kind of mucky up the waters. No, because you know everything has to be converted. But no, let's just keep with K. We're just going to keep it simple because we're just talking about your statements. We don't need to get into the weeds. Okay, IJK. So it would be something like this because we wouldn't know what I was when we're writing this program. We're writing it to be dynamic and to be able to use multiple input types and pieces of data as it processes. So we'll say something like I is less than K. That's where it would get kind of more like what you would see its real use case being. So the compiler would go in and evaluate, hey, is I less than K? 0 is not less than 2, so it's going to evaluate that as false. Now, by the way, if I take this, because I just started this up in debug mode, if I take that and say add watch, notice down here that I less than K, it's going to evaluate as false, but it's actually not going to, that's just by default. Because those values haven't been set yet. Okay, and that's kind of what you would see normally for an advanced program. And so that works with greater than or equals, if I is equal to K, that's a comparison. But let's get a little bit nutty. Okay, so let's look at plus 4 minus 2 divided by 2 times 3. Okay, that's a little nutty. Okay, let's see what we got over here. Okay, plus 2 minus I divided by, what do we have up there? J times 2. Okay, I have no idea what it's going to do. I have no idea. Because we're getting a little bit nutty, and so I'm trying to show you a little bit of the complexion that this can have because I'm mixing relational operators with normal operators. So what happens first? How does this get evaluated? Because a computer can only do one thing at a time. It's not, and you learned in math, everything has a priority in your order of operations. And we call that order of operations. So what is the order of operations? Just like what you learned in school. But we actually have a table that's followed for order of operations. And if we look, we just need to determine, hey, what kind of operators do we have? We have a relational operator, the less than here. That's the only relational operator. And we have some processing operators, multiplication, addition, negative. So what is evaluated first? Is the less than done first? Or is it the traditional math that's done first? And we can go to our table for that. And you see here that you see how plus minus is below times divide, like it should be. Let me zoom in on that. So you're not, because I'm sure your nose is touching the screen right now. Jeez, mine is actually. Mine was. I was like, woo, okay. But you see how much higher in precedence the normal math has to the relational operators. And you see here that then we got some structure. We know that times multiplication and division happen first. They're highest in priority. Plus minus happens second. Lastly, are relational, less than, greater than. Okay, let's break it down. All right. What we're going to do is we're going to evaluate it for fun. And then we're going to control Z and test it. Just to, I might just totally screw up and make mistakes. I've made videos where I make this mistake. I keep it in because we still do it. Yeah. So we'll see if I make a mistake. Well, let's look at our operators here. What should happen first? Because we know that division and multiplication are highest on the precedence. But which one should happen first? And that's where you go to the associativity. So the associativity, the precedence and associativity for these guys is left to right. That means that the ones that happen first are left most. And of course, top-down is top-down programming, so everything happens mostly top-down, left to right. There are some operators where we want to work in the other direction, but I'm not going there. So we know that this is the first division operation. Okay, so what does that express at? 2 divided by 2 is 1. Okay, 1 times 3 is 3. And this is all happening behind the scenes. You don't have to see it because the compiler has written the machine code for it to happen. And this one line is probably about 50 lines of machine code. You're just doing this one at a time, throwing it at the CPU. Every process that I'm showing you up here has been thrown to the CPU in order of operator precedence and associativity and flow top down. That's how it's getting pushed onto the CPU. So the next process that the CPU handles is 1 times 3, which is 3. Then we have the next process, which is 4 minus 3, which is 1. Then we have, oh, I screwed up. Oh, you're like, Mr. B, you screwed up. Uh-oh. What did I do wrong? Oh. Yep, messed up. Okay, 1 times 3 is 3. But I'm forgetting about these guys over here, aren't I? Yeah, I am. Okay, so these guys are on hold because this guy has the leftmost highest precedence. So we've got to do I divided by j. So I divided by j, 0 divided by 3 is 0. 0 times 2 is 0. Now, since the operator precedence, the associativity is left to right, precedence is done because we only have now the same tier or precedence operators left, plus minus. So now we go over here and we do I plus 4. So I is 34, so that becomes 38. 38 minus 3 is 35. Okay, k plus 2 is 4 minus 0. So is 35 less than 4? No. Last process, 0. And then the very last process that's pushed onto the CPU is a comparison. Are we at true or false? Oh, we're at false. Therefore, the next process we're throwing at the CPU begins on line 22. And we skip lines 17 and 18. And that is how it's done. What am I I doing here? Oh, yeah, we're going to control Z. Oh my goodness. Control Y is redo. I lost the whole thing, so we can't. Is that the whole thing? There we go. Okay, hopefully that was the whole thing. We're going to find out. Okay. So let's debug it. And if I just want to, kind of see what's going on here, I can do a step over, get to here, and then I can just select this side, add watch. So all those together comes out to be the value 1. So I did something wrong, very wrong. Okay, so this goes over here. Let's do this. Add watch. 4. All right. Add watch. True. What did I do wrong? Okay, well, we know this has to evaluate to a 1. So let's look at this again. 2 divided by 2 is 1. 3 times 1 is 3. 4 minus 3 is 1. What's going on? I can't figure it out. Oh no. Very common thing that happens. And this is actually exactly the type of thing I like to point out. And kind of back to the discussion of the last PowerPoint. See this little I divided by j here? I is 0, j is 3. Let's hover over that. Oh! In my mind, I had that wrong. Because what did I do to I? 34. I bet you watched that whole bit where I messed up and didn't oh, okay, whatever. But what did I do to find out where I went wrong? What I did is I went into the debugger and I started doing these things and looking at them and adding a watch. And then I came to here and I added a watch. I said add watch. I selected that. And it shows up as 11. I'm like, what? I didn't calculate it as 11 when I did it in my mind. Oh, well, not sort of in my mind, but, right here with you. And then I looked up here. Oh, duh. The compiler or the computer will always do what you tell it to. And that's what the debugger is for. It's for those little moments. So let's redo this. We know that this came out as, and we're going to cheat on this one. Let's go to here. Let's cheat on this one. I think we added this one up, right? Yeah, 35. We had 35. Okay, so this comes out to 35. Now let's redo this one. I divided by j. I is 34. J is 3. But we got to remember that we are dealing with a integer, and it's going to truncate it because we're not assigning it to a float where it will graduate. So it's going to take I, which at this point 34, divided by 3, 11.33, and the 0.33 gets chunked out. So that turns to negative 11. Left to right, k plus 2 is 4. 11 times 2, negative 11 times 3 is negative 22, which is negative 18, and 35 is not less than negative 18. So let's see if we got it right now. Oh, God, Ellie. Oh, jeez. There we go. I think that was it. All right. Add watch. Negative 18. Okay. And it's false. If statements can be totally nutty. Totally nutty. Okay. That's not it. We're not done because I'm going to add more to the fire. What if we wanted to have multiple different relational operators that we compared? And that means that we can do and or. Okay, so those are called logical operators. And they're often paired with if statements so that you can make the if statements more complex, where you pair multiple relational expressions together. So let's look at what that looks like. What does that look like? And then, guys, we're going to do some a breeze through on the rest of your PowerPoints because this is the big kahunga today for this chapter is learning these. I'm narrowing in right on what matters. The other stuff, the other little bitties, I'm going to leave up to you in your reading. Okay? So let's look into this. All right, we're going to do some scribbles. Scribble, scribble, scribble. All right, what we're doing is I am showing you, oh my God, I hit it again. Stupid thing. It always messes up my pen. Okay. Yeah, I'm showing you how logical operators relate to relational operators. And what logical operators are is they just put together relational operators. So, our relational x is less than y, and how do we combine that with another relational operation, like maybe x equals 3 or something? What if we wanted to find out when x is less than y and x is equal to 3? That's called an AND operation. That's a logical operator, and we use 2 of those symbols, ampersand symbols. Those are pitiful ampersands. This one is the most pitiful ampersand, but we use double ampersands. Okay, that's my first name. Oh my God. Okay, those are ampersands. We use them to put those relational operators together. And the way it works is just kind of how I worded it. When we use an and is when we want to see if something is true and another thing is true or false. And we can really abstract it down to where an and operator has lower precedence than these guys. That means that these guys, these relational operators, happen first. They happen first, and then the logical operator happens. Which makes sense because if you're trying to find out when x is less than y and x is equal to 3, the relational operators have to happen first. And if you look at the operator precedence, you'll see that indeed the logical and the logical or happen or at a lower precedence than your relational operators. So then what does that look like? This is an or. That means if you want to say if x is less than y or x is equal to 3, then the whole thing is true. Um, and let's go back to the whiteboard here. So you have the or statement. And so we can actually abstract these down to just true or false. Now remember, I'm using 1 is equal to true here when I'm laying out these truth tables that I'm going to, for the logical operators. And that one is equal to false. Remember that, okay? All right, so for the and operator, when you pair it with, now remember here, these guys are going to come back with a 1 or a 0, a true or a false. Those guys, these relational operators are going to return a 1 or a 0, a true or a false. A true or a false. And then that is what's then evaluated with the logical operator. So the only thing that the logical operator is looking at is true or false. True or false. That's what the ampersand, the logical operator, is looking at. So the truth table is when we have a true and a true. I'm just going to put the word here and a true, a 1 and a 1, then it evaluates as a true. So that means that if x is true and if x is less than y, that comes out as true, and x is equal to 3, that comes out as true. That means that we have a true and a true. That evaluates as true. Now, with the and operator, that means then both operands, the result of the relational operator, have to be true for the whole thing to be true. So if 1 is false, like a 1 and a 0, a 1 and a 0 is a false. Because when we use that term and, we mean both sides. This has to be true and this has to be true for the whole thing to be true. Because the last thing we do is we put it through the AND gate, the logical AND gate on the CPU. Okay, then we have a 0 and a 1. That means the first one is false and the second one is true. Well, again, they both have to be true for the whole thing to be true. And the last one is when they're both 0. And we know that that's false. So with the or, this is the or now. A 1 or a 1 is equal to a true. A 1 or a 0, because remember, this one is or. This one has to be true over here. Over here. This one has to be true, or this one has to be true. And we're talking about the or operator now. Or. So get rid of this in your mind. So this one or this one has to be true for the whole thing to be true. The whole thing. So 1 or 0 is 0. A false or a true is, oh wait, no, I messed up, is a true. And a true. And then a 0 or a 0, that's the only time that an or operation comes out as a false, is when all of them are false. So only one has to be true to make it happen. So 1 or 1, 1, 1 or 0, 1, 0 or 1, 1. So this is the same thing you learn in like a logic class that you would take. at the 300 level, something like that. And you literally just use words. It's not a programming course. It's just all about this kind of crap. Yeah. So let's look at that. What how does that change things over in the code? Well, let's simplify this first. I is less than 50, 60, whatever. I don't care. Let's get rid of this. Okay, and the way you do it is we're going to do an AND operation first. And I is greater than 0. Let's say we want a number between 1 and 59. That's what we would do. So the only time this is true is when each side is true. So let's see what happens when we set I equal to 34. We'll come in here. This one says, hey, is I 34? Yes, it's less, or I is less than 60. Yes, it is true. Boom. This does not happen yet. Then it says, hey, is I greater than 0? Yes, it is. Awesome. True. Now this can happen. 1 and 1 from our truth table is a 1. True. Yes. All right. What does that look like with 0? I is less than 60. Yes. I is greater than 0. No. What is 1 and 0? 1 and 0 is a 0. So that would be false. Okay. Let's do this with an OR. Now this is kind of an oxymoron because it's always going to be true. Because any number is greater than 0 or less than 60. Pretty much most numbers. And then since we're using an OR, this logic really kind of dies. So let's modify this to something like a little bit different. Let's say that if I is less than 0, or I is greater than 80. Okay. Let's try it with a -2. Yes, this one is true. This one is false. 1 or 0? 1. That one would be true. Let's try this with a 45. Okay, so this would be false. This would be false. Right? Yeah, false. 0 or 0, that's a false. So you see, this is going to be a false for any numbers between 1 and 79. And it'll be true for anything else, I think. So it gets nutty. Yeah, okay. So here's where it goes next. You can do this. And 4 is less than k, or j, or whatever, 3 minus 6 divided by 4 times 4 equals, oh no, is less than 0. I don't know, whatever. Okay, so now you see what we're doing. We're chaining them together. And then we can do an and. For greater than, let's just do I, something like that. Okay, so this is where things get kind of crazy. So how is this evaluated? Well, we know that all these guys are going to be done first. Boom, 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 boom. Done, done, done. They're going to all evaluate to true, and then it just gets to these guys, the logical operators. But what happens first? Which one? And that's where we go to dun, da, 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 operator precedence and associativity chart. You see how the ampersand is higher than the ors, the and has higher precedence over the or, and it's left to right. So the and happens first. So this one happens first. Then this one happens next. And I'm just making up these values. Oh, this has already happened. What? Oh, wait, what am I doing? Now, then this one happens. And then this one happens. And then our flow continues on. All right, guys, that's the big kahunga. Yeah, maybe that's dating me. I don't know. Whatever. It doesn't matter. I don't care. Okay, so let's. I think we've got to the main. I mean, this is the big ideas that I had, that I usually go over with students for the parts that they have the most trouble with in this chapter, and also some of the comprehension that they don't understand of the complexities that can happen with relational and logical operators, and then to become familiar with operator precedence and associativity, and to really drive home the use of the debugger. Use it, please. Okay, let's just do a lightning pass through PowerPoint. Okay, we've talked about, you can. Let's see if we're missing, anything really heavy duty. Most of this stuff you can kind of figure out on your own by using the debugger. Here's what I want you to do. This is going to be a little video homework. I want you to find an example of a switch statement. And I want you to set a breakpoint at the beginning of the switch statement. And I want you to test different values, and you can just hard code the values in for your expression, and walk through and use the debugger to examine how switch statements work. And then I want you to consider what is called a fall through switch statement. That is one of the most efficient control structures you can develop. It's what everybody tries to go towards when they're trying to make their code faster. So examine how a switch works and how fall through works. So do that before you move any further. And I think this is enough time before we go to modeling a programming problem. So that's where we're headed here very shortly. Okay, it's time. We're going to go talk to Sandra. Hello, Sandra. How are you today? Let's see what she's got for us. Hi, Sandra. You hear me?
Hey Josh, I can definitely hear you loud and clear. How's it going? Let me know what you're working on today.
Uh, well, I'm actually doing a video with my students, and I would like to model a programming problem with them. Can you give me something, some like maybe three examples of programming problems that would be given to a student for like maybe the control structures chapter in an introductory course? Uh, I would like it for it to have some logical operators and of course relational operators and a little bit of complexity but not too over the top. And when I get off chat here, off live, I'll tell you that I'm ready for the list of at least three. Can you do that for me?
Absolutely. I've got you covered. I'll put together a few examples that use control structures, logical operators, and relational operators, but keep it at a nice introductory level for your students. And whenever you're ready, just let me know and I'll run you through them.
Okay, thank you, Sandra. Hi, I'm ready. Come on, Sandra. Jeez. Oh, come on. Yes, please give me the programming problem examples or prompts or scenarios or whatever. She's gonna drive me nuts. Actually, she is driving some people nuts, really. Okay, let's see. Caffeine converter. Ooh, good pick. Oh, that's me. That's so me. Yeah, we're not going any further. We're doing this one. Okay, cool. Um, let's just throw this up here so I kind of know what I'm doing. Oh, let me get the stupid whiteboard out of the way. Okay, let's get serious now. Cool, 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 cool. Now this, what do we need to do? Input. Oh my goodness, look at Sandra. She's so good. She already knew that I wanted input, process, and output. All right, we already got it. This is great. Amount of caffeine in milligrams. Okay, let's just do that. So we know what kind of variables do we need. Well, it's right in our input, amount of caffeine. So let's do this. Now, is that a whole number? It can be a floating point because you can have fractions of milligrams. So I'm going to go ahead and make that a float. I don't want to do a double because I don't need a big number. No need to be wasteful. And then I'm going to just call it, okay, float. My insert key did some things to me. Float uh, amount of coffee. Okay. That's kind of how I like to code. I like to do lowercase, but be very explicit. I don't like to use a lot of undercases. Um, so, yeah. I don't like to use uppercases because I'm lazy. No, I'm not lazy. Really, I'm not. Oh, no. Okay. See out. Please enter amount of coffee you have drank. We're going to call this the jitter relief. I'm going to say, yo, dude, you got the jitters? How much? How much? Yep, CN. Amount of coffee. Okay. Now what's the process? Assume half-life of caffeine is 6 hours divided by, you know what? This is ridiculous. She didn't put in, this is where Sandra dies. I just got too excited. I didn't even check. Could you extend or modify the caffeine one so it uses if statements and logical operators? All right, so there we go. That's more like it. Okay. So not too far. Okay. Let's see how this scenario plays in to what we're going to actually do. Okay, so this is going to be all right. Amount of caffeine and then half-life and then how many hours. So this, oh, this is cool. This is like a junkie's cheat sheet, not to get too heavy, but still maintain their habit. God. All right, so we're gonna use if statements. We're gonna input how much caffeine, how many hours ago, and we're going to use if statements and math to determine if they should continue. This one's going to get involved though. This one's going to get kind of crazy maybe. Let's see. Let's get into it though. Hours ago, caffeine, and let's do this. I think I'm good on what we need to do. So since we're doing calculations, definitely hours since. Okay, and let's and you want to be very explicit and put F there because that means floating point. Otherwise, it puts in a literal double instead of a floating point. Yeah, weird. But you don't have to put the F. Amount of coffee, see out. Hours since equals 0. Equals CN. Nope. See out. See out. How long ago? Okay. CN. Hours since. Okay. Oh, I put the S together. Okay, that's fine. Half-life of coffee. This is where we want to break up into smaller parts a little bit. Let's do our logic first. That means we're going to look at the current level of coffee in a person's system in milligrams and determine whether they can drink more. And that's all we're going to worry about. And we might put an hours since and and in there, just to add some flair. Let's say that we're going to do based on hours as well. Based on hours, if we can do some math with that. Let's do the logic first, and then everything else will come from that. If, and so we're going to be doing a calculation on, amount in body equals 0.0 F. And then all the logic is going to do is say if in body. Now, what is the scenario calling for? A 100 milligrams. Okay, so if it gets down to 100 milligrams, and then let's put in something that deals with hours. So like, let's do milligrams per hour. Or based on 100 milligrams in body, or milligrams consumed per hour is greater than, and we can tailor this just to see the differences that things will come out. I want to just demo the use of the if statement. I'm not really caring about the math because we're just having fun here. Yeah, but this adds in the logical operator that Sandra, you're in trouble, Sandra. You didn't get it right first time. I got all excited when you said caffeine, and I delved into it and got too far before it was too late to turn back, and now we are having fun with this. And it works out. So let's say if in body is greater than 100, and we're going to do 0.0 here, F, because we want a literal floating point number. If we just do 100.0, it defaults to a literal double, which is 8 bytes instead of a float, which is 4 bytes. So we're just being more efficient. That's all. We're putting in a literal F, so the compiler doesn't have to do an implicit conversion from a literal double to a float. And we always want to do that, especially when we have the compiler degraduate variables. So if we start out with a literal double, okay, I'm done. Yep, we're moving on. Yeah, I can get into the weeds better than the best of them. All right, in body greater than 100. Now, what is it that we said? Or milligrams consumed per hour is greater than 50. Or mg per hour is greater than 50. Now then, oh great, we've got amount of coffee and mg per hour now. No, in body. Let's change this because that's not good. Coffee, I'm already getting it mixed up between which is which. And then let's do float, coffee, in body per hour. Okay, so yeah, I'm not really actually lazy at all when I do it this way. Okay, so now we're going to say if coffee and body is greater than 100, or coffee and body per hour is greater than 50.0 F. See out, and if it's only one liner, you don't need the scope, the braces, guys, the squigglies. If it's just one liner, nope, no go, dude, none for you. Okay, then we do an else, and again, if it's just one liner, we don't need to do the braces. See out. Yes. Drink on. Okay, so that kind of puts it together. Now, what do we need to actually process? Now I did a part of it, and that kind of gels it in my mind what I actually need to process because I've already done the logic. So I need to find what coffee and body is based on the user's input, and that's going to be based on the half-life of the hours. So what is the scenario half-life? The coffee, 6 hours. So the amount halves. So every 6 hours, the amount halves. So that's going to be, no, I think what we can do is just do amount of coffee, or coffee and body, and you know what, guys, this might not even make sense, and I don't care because your scenarios will be much more detailed on exactly what you got to compute. So I'm going to compute coffee and body as amount of coffee, and we're going to take the amount all right, I'm going to do some storming. I'm going to do some brainstorming. determine how we're going to add the amount of half-lives that need to happen mathematically with the POW. And so we're going to do the amount of coffee in the body, and then it's going to be based on the amount of coffee, and we can multiply that and have it be a reduction. If we multiply it by a power of 0.5, so if we multiply the amount of coffee by half, 1/2, it's going to divide by 2. And if we take that half and we determine the amount of times of half-lives by this thing, then we know how many times we need to multiply the amount of coffee in half with the POW. So we can just do this, multiply, and we're going to use the POW function, which is the power of, and here we're going to say multiply the amount of coffee by 0.5, and I want you to do it this many times. And so this actually is the kind of math I don't care for, because I'd rather do this in a loop, but we haven't learned loops yet. And I did go on to chat GPT change it, so we're just, okay. So that's going to be the coffee in the body. So if it's greater than 100, then nope, no go. But if the coffee in the body per hour, how is that going to do? That's going to be amount of coffee. Okay, so coffee, and I'm just going to wing this one. Coffee in the body per hour is equal to amount of coffee divided by hours cents. Okay, now it's time to test and compile. And it looks like I messed up here. So I'm going to do Control S, save it, and then I'm going to go up here to build, rebuild, or you can just hit F5 or, oh, I'm still debugging. What an idiot. Okay. Writing code while you're debugging. Stupid. Okay. All right. So it's compiling. We can run it through its paces. I'm going to set a breakpoint. Guys, use the debugger. Just saying, just a little side. Use the debugger. You're going to get sick of me saying it. You are going to get sick of me saying it. All right, so I've just stepped over, and now I'm at this line. Which one am I actually running? This one right here. Okay, so I need to, did I step over yet? I need to step over this line. Then I go to my input. Okay, so I'm going to say, I'm going to be just, I don't know how our math is going to look. I'm going to do 1,000. Okay, now I got to go over here again, and I got to step over. Okay, now I got to see in how long ago? 4 hours. Okay, let's look at that. Let's see what happens. Amount of coffee. So look down here. So you see we got all these variables that I threw into the messing around earlier. I'm just going to delete that all from the watch. And I'm going to go to locals. Here's all our locals and what they have. Hour cents has 4. Amount of coffee has 1,000. So we're good. So I'm going to step over, and I see down here, half-lives is 0.66. So we're going to have a half of a half-life. Okay. So I don't think coffee and body, I don't think it's 629. I think this dude is screwed. Yeah, he's not going to be able to get any more. Nope, none for you, dude. You're screwed. Okay. Okay, so then let's do this. Let's try some different numbers. And let's do this. Let's set the breakpoint right here. And I want to see what happens when I try to break this if statement, because there's a place where that coffee and body per hour math is probably not going to work out too well with the mathematics of the coffee and body. So, yo, you got the jitters? Let's do 200. We're going to be conservative. How long ago? 4 hours. Okay. 50 coffee and body per hour is 50. Did I get it right off the bat? Coffee and body per hour 50. Okay. Okay, coffee and body is 125. So I still didn't get to the sweet spot where I'm testing that ore. Okay, so let's do this. 120, 2 hours ago. Coffee and body is 95. Coffee and body per hour is 60. Cool. It worked. The math worked out. Okay. So you've been drinking too much per hour. That might be a measurement of, maybe if you're having too much of the coffee in your stomach per hour, maybe a sign of how much acid you have, and you want to say no, you've had too much acid or something like that, whatever. So nope, dude, none for you. Okay. When do I get to drink my coffee, man? When do I get? Come on, give me my coffee. And let's see. 100. 3 hours ago. Yes, drink on. Woo! Okay, I don't know where it broke. Where it's coming in on that, but that's kind of an example of what you're going to see and be dealing with. Do your best on the math. It is important. That's it, guys. I mean, an hour and a half is good enough. I'm hoping you took breaks and maybe came back to it after a while. But yeah. All right. Take care.